Now we will discuss a very important phenomena which is associated with the surface tension, or you can say where the surface tension will play a key role. That is called capillary action. What is capillary action or capillary phenomena? What is capillary action? See, whenever you immerse a tube of very small cross section radius, whenever you insert a tube of very small cross section radius into the liquid, when you insert a tube of very small cross section radius, extremely small cross section radius into the liquid, then you will find that if suppose it's a glass tube, then if this liquid wets this glass, then the liquid will rise up, and if this liquid does not wet this glass, then in that case the liquid will go down. If the liquid wets this material of which the tube is made, this is a tube of very small cross section radius, and if this tube is immersed, and suppose this tube is made up of glass, then if this liquid which you have over here is a wetting liquid with respect to this glass, then this liquid will go up in the tube. It will go up, it will rise up in the tube. And if the liquid over here is non-wetting, then in that case the liquid, instead of rising up, it will go down. It will go like this. Inside the tube the liquid will go down. The surface is this is a liquid surface, and the liquid inside will go down. It will go down. Whereas if it is wetting liquid, then the liquid will rise up. Liquid will rise up. The level of liquid in the tube will be higher than the level of liquid outside the tube. Whereas in case of non-wetting liquid, the level of liquid inside tube is lower than the liquid layer, the surface of liquid. The level of liquid inside tube will be less than the level of liquid outside tube, right? So that is called capillary action. This is called capillary phenomenon or capillary action. When a tube of very small cross section radius is immersed into a liquid, then the liquid will rise up if the liquid is wetting with respect to the material of which the tube is made, and if the liquid is non-wetting with respect to the material of which the tube is made, then the level of liquid will go down, and this is called capillary action. This is called capillary action. Inside tube, if I magnify this, then if it is a wetting liquid, then your meniscus, the liquid will not be straight, it will be like this kind of thing, and this is called meniscus. This upper surface of the liquid will be of this kind. If it is a wetting liquid, suppose you have a water, the good example of this case is you have a glass tube and the liquid is water. The level of liquid will go up, and you have this kind of meniscus. You have this kind of meniscus. This is called meniscus. The upper surface of the liquid, it is of concave shape, right? So this is called meniscus. This is called meniscus. So you have concave meniscus in this case. And the good example of this case would be, if suppose this is mercury, this is glass tube. So if you dip a glass tube, if you immerse a glass tube in the mercury liquid, then the level of mercury will go down, and in this case, since it is non-wetting, it will have a convex meniscus. It will look like this. Here if you magnify this, it will look like this. It will be having convex meniscus. And the reason I have already discussed in the last video, that since this is wetting, it will try to have larger interface with the solid, since the adhesive force between the liquid molecules and the solid is higher compared to the cohesive force among the liquid molecules. So the liquid will try to stick more and more to the surface, and it will have this kind of meniscus. And in this case, mercury, inside mercury, you have cohesive force is very high compared to the adhesive force between glass and mercury. The cohesive force among the mercury atoms is very high compared to the adhesive force between glass and mercury. So mercury will try to have less and less common interface, or less and less it will try to be having less interface with glass, right? Since it is non-wetting, it doesn't the inside, the force inside mercury is higher compared to the force between mercury and glass. So mercury will try to have less and less interface with the glass, and hence it has got this kind of thing. The mercury tries to contract away from the glass, doesn't want to be in contact with the glass. It tries to keep itself away from the glass, and hence you have this kind of meniscus, right? Okay, now the big thing over here is why we have such a thing happening, why the water rises in the glass tube, or why the mercury falls in the glass tube. We have to look into the reason behind this, and then we have to calculate what is the height of water which rises in the glass tube. What is the height of water which rises in the glass tube, and of course what is the height of mercury, what is the depth of mercury below the surface of mercury outside. What is this depth? What is this depth? We have to calculate all these things. So let's reason out why we have this water rising inside capillary, and this is called capillary tube. This is called capillary tube, and hence it is called capillary action. So let's discuss the reason behind this. Why capillary action? Why capillary action? First, let's just draw the figure of the capillary action. Suppose this is the liquid. Suppose this is a wetting liquid. This is a glass tube. So the level of this wetting liquid will rise up. Suppose it is water, and you have this kind of meniscus getting formed. Since it is wetting liquid, it will try to have more and more contact with the glass. It will try to have more and more contact with the glass. And since you have this kind of meniscus, this meniscus is the curvature of this meniscus. This meniscus is just like a kind of hemisphere kind of thing. So in this case, due to this curvature, as we have seen in the topic of curvature and excess pressure, the pressure in this kind of curvature, the pressure over here is more and pressure over here is less. In this case, this develops an excess pressure. This develops an excess pressure on this side. We have already seen this, that if you have this kind of curvature, then surface tension acts like this, and this force due to the surface tension. See, when you have this kind of meniscus, if I only consider this part, you can see over here that you have this kind of meniscus. So it will try to you have here this is meniscus, this is liquid, and it will try to pull itself. The surface tension, the force due to surface tension on the glass acts in this direction, and as per Newton's third law, the glass will exert force TLV in this direction, right? This liquid try to decrease surface area, and in that process it pulls the glass with certain force, and glass pulls it with the equal and opposite force, right? This the glass will pull the liquid. The liquid try to pull the glass. See, liquid in the process of decreasing, it has got a tendency to decrease surface area due to surface tension. The liquid has got a tendency to decrease its surface area, and in that process that's called surface tension. In fact, in that process it exerts force on the glass with which it is in contact, right? And the force per unit length is, that is TLV, force per unit length acting on the glass is TLV, and hence glass will also apply equal and opposite force TLV. This is the force per unit area. This is the force per unit area acting on the liquid, right? And this force per unit area acting on the liquid, and these forces, see, this force will act at every place, at all these points. At all these points, these forces will act, right? I'm not drawing it. I've just drawn at 2 points, but this force per unit area will act at all these points. And this is your if I draw this horizontal, this is the angle of contact. So the horizontal component will cancel out and vertical component of these force will add up. The horizontal component, they are going to cancel out, and the vertical component will add up, right? TLV sin theta will cancel out, and TLV for every point over here, we have a point over here, such that TLV sin theta over here and TLV sin theta over here will cancel out, and TLV cos theta will add up, right? So the net force acting on the liquid is TLV cos theta, where theta is the angle of contact, into this length, the circumference, and suppose the radius is r, that is TLV cos theta into 2 pi r. So due to this force, the liquid rises up. The liquid rises up, and it will rise till this weight of the liquid becomes equal to this. It will rise till it comes in equilibrium. And when does it come in equilibrium? Till this force acting in upward direction equals to the weight of liquid which is lying in this region. So weight of this liquid will be how much? If I neglect this meniscus part, then I take this height, say it will be rho into and what is the, if suppose the height gained is h, neglecting the meniscus, then this will be rho into volume is pi r square h. Alright, so h will be 2 TLV cos theta, pi will cancel out, and here you have rho and g also, of course, rho gr. That will be the height of liquid in the capillary. Height of liquid in the capillary. Getting a point? If I also consider the liquid which is below the meniscus, here I am neglecting the meniscus. Here I was neglecting I was calculating height only till this. I didn't consider the liquid which is below the meniscus, right? This liquid, see, I'll try to have a better figure. Here I didn't consider the liquid which were lying in this region. Liquid which was lying in this region. I consider only liquid which are below the lowest point of meniscus. So if I also include this liquid, then volume would be higher. Then in place of this, I'll write rho into, what will the volume in that case? Pi r square h plus this volume. What will be this volume? See, if I consider this to be a sphere, hemisphere, then this volume would be how much? This volume would be, first of all, I'll calculate this volume. Suppose this is hemisphere of radius say r, then this will be, this volume would be the volume of this cylinder first minus this volume of hemisphere, which is pi r square, and this height will also be r, minus, so that will come as pi r cube by 3. So this will be plus. So in that case you have H plus R by 3 as and say rho and G also over here, GR. Alright, so this way you can do it. You can also express this TLV in terms of height gained by the liquid. This TLV would be equal to rho GR H plus R by 3 upon 2 cos theta plus surface tension in terms of height gained by liquid in this way. Alright, get your point? And one more thing, see, I told you in the last video that in case of wetting liquid, this theta is acute, whereas in case of non-wetting liquid, this theta is obtuse. So over here you can see this cos theta comes in numerator. So for wetting liquid, theta is acute, so cos theta would be positive and H would be positive. That means wetting liquid gains height. And for non-wetting liquid, theta is obtuse, that means cos theta will be negative. So H will be negative. H negative means what? The liquid is going to subside. Liquid is going to subside by a distance of H. It will go down. In case of non-wetting liquid, you will find that in case of say mercury, if it is mercury instead of water, if it is mercury, then H will be negative, and that will be the depth by which the mercury will go down. That will be the depth by which mercury will go down. Alright. In case of wetting liquid, there will be capillary rise, and in case of non-wetting liquid, there will be capillary fall. And this is H. Right. If you neglect this theta, sometimes people also write it as 2 TLV by rho GR. Right. Sometimes people write like this also. Now, what will happen if suppose I have a case where say we have this is the container, water container, and say we have say water over here, and I dip a capillary tube. Now suppose the height of this capillary tube is not sufficient. Suppose this height of capillary tube, this is not sufficient, means suppose for example, as you dip the capillary tube, the water will go up, and height which we are calculating from here, say this height, this is the height by which water should rise up, and suppose the height of capillary tube above this water surface is less than this height. Suppose the height of capillary tube above the water surface is less than this height. Get your point? This is the height by which water should rise, but height of capillary tube above this water surface is less than this height. And what will happen? One thing comes to mind, that water should fall. If suppose the water should rise in capillary given the surface tension theta and all those things, suppose water rises by 10 centimeter, but height of the capillary tube available is say 8 centimeter. If suppose water should have risen by 10 centimeter, but the height of the capillary tube available above the water surface is just 8 centimeter. In that case, what will happen? Will the water fall? It never happens. Why? See what will happen. Suppose this h is less than this. Suppose this h height which is available is less. Suppose the height which is available is less. See here. See one thing. See the height by which the water should rise. Suppose I call this h dash. Suppose I call it h dash. Right? H dash. H dash is less. So height by which the water should rise is given by this, and this h dash is less than h. H dash is less than h. See what will happen. I'll tell you. This is the height by which water should rise up, and h dash is the height of capillarity which is available, and this height of capillarity which is available over the water surface is less than the height by which water should rise up. In that case, see what will happen. In that case, see what will happen. See, inside capillary tube, the meniscus, let me discuss what meniscus which you have. See, this is your, just consider meniscus, the kind of meniscus which you have. See, water sensitive wetting liquid, it has got a concave meniscus. Concave meniscus. So this is your what? This is radius of capillary tube, and this is say a part of sphere. Suppose the radius of curvature of this is, how do you find radius of curvature? You just produce this surface and make a complete sphere, and then find a radius of that sphere. See, this may not be a complete hemisphere. This may not be complete hemisphere. It may be less than hemisphere. So you just produce this spherical part and form the complete sphere, and the radius of that will give you a center of curvature of this surface, and radius of that sphere is going to give you radius of curvature of this meniscus. Radius of curvature of this meniscus, right? So this is radius, suppose. So this is radius means this is small r and this is capital R. And what is this angle? This angle is theta. This is 90 degrees since it is tangent. So this will also be theta. This will also be theta. So can I say that R, radius of curvature, capital R, cos theta is smaller? We can say this. This is tangent, this is angle of contact. So R cos theta is smaller. This is radius of capillary tube. This is radius of curvature of meniscus, the angle of contact. Or you can say R is R upon cos theta. So what I can write over here is, this is 2t LV and rho g R upon cos theta. That is 2t LV rho g capital R, where I is the radius of curvature of meniscus. So that is your h, height by which the liquid should rise. And now I take R on this side. So height of water inside capillary tube into radius of curvature of meniscus will be equal to 2t LV by rho g. And given a system, this is going to remain constant. So if suppose you have height h dash less than h, then what will happen is water will rise till height h dash. Water will rise till height h dash, this kind of meniscus, and thereafter what will happen is this meniscus, the radius of curvature of meniscus, this meniscus which was concave, will start getting less and less concave. It was this could have been meniscus. Then after reaching h dash, the surface will try to become flat, not exactly flat. It will depend on the value of h dash. So surface will start getting flatter. So as the meniscus start getting flatter, the capital R increases. Capital R increases, radius of curvature increases, as the concave meniscus start getting bit flatter, in that case the radius of curvature increases. And by what will, till what time radius of curvature will increase? Till h reduces to h dash. So what will happen is, it will go till h dash, then capital R start increasing till h become equal to h dash. So when capital R increases, of course h will fall. If capital R increases, then height by which water should rise will fall. So capital R will start increasing, it will increase till the height by which water should rise falls to h dash. So water will not split away, water will not spill over, it will go till height h dash, and if h dash is less than h, in that case the meniscus will start getting flatter, radius of curvature will keep on getting high, and radius of curvature will keep on increasing till h become equal to h dash, because the product of these two is constant. See, one rises, one has to fall, the other has to fall, alright. So this is how it goes on. Water does not spill over, the meniscus become flatter if the height of capillary tube is insufficient, alright. So this is how we can explain the why the height of water rises in the capillary tube, alright. There are a few things which I'll tell you over here. What are the factors affecting surface tension? See, if I contaminate the liquid, if I dissolve substance into, if I dissolve some substance in liquid, what will happen to surface tension? See, if solubility of that substance is higher, means the force of interaction between solute and the liquid, cohesive force between solute and the liquid is higher compared to the, also it's not cohesive, you can say adhesive force between solute and the liquid is higher than forces which the liquid molecule exert among themselves. In that case your surface tension will rise. And if solubility is low, in that case surface tension is going to fall, right? So that is one thing. If you dissolve certain substance and solubility of that substance is higher, in that case surface tension is going to rise, and if solubility of that substance is low, in that case surface tension is going to fall, right? Similarly, surface tension has got dependence on temperature also. Surface tension decreases as the temperature rises. You can say this is T, surface tension T is T naught 1 minus alpha T, where T is surface tension at T degree centigrade and T naught is surface tension at 0 degree centigrade, and alpha is temperature coefficient of surface tension, right? So you have two things which are important, all right.